Okay, here we're going to talk about the definite integral and the fundamental theorem of calculus. It's just our acronym right up here, the fundamental theorem of calculus. And remember, we defined the definite integral, and remember also that definitions are just an agreement, right? And we just said if we have n rectangles to approximate the area, and we take the limit of infinitely many, or as n approaches infinity as the number of rectangles, we're going to get the exact area. And we're saying that the definite integral represents that. Now, there's a lot of mathematics linking that idea to that area. And we must also be aware that the area also, it's an interpretation of area because if we interpret it, as such where the function is below the x-axis, then that would give us a negative height, right? So we have a function that goes above and below the x-axis, then it's going to be the area bound by the function above the x-axis, but we are going to subtract the area below the axis or below the x-axis, simply because, again, we're getting negative heights here. So we'll talk more about how that relates and when we want the total area in the next video. But right now, we're just going to focus on evaluating these definite integrals. And that's where the fundamental theorem of calculus comes in. And really what this is saying is that all we need to do is take the antiderivative, and we did that when we were working with indefinite integrals. We're going to evaluate the antiderivative at b, which is this upper limit, and subtract from it the lower limit, okay? So if our region goes from a to b here for our definite integral, okay, really we just have to evaluate the antiderivative at each of the endpoints and take their difference in this order in order to get the evaluate the definite integral. Okay, so that's the beauty of the fundamental theorem of calculus. And there's a lot to it. If this was a more theoretical course, we would take a look at the proof of it and so forth, but we're not going to do that in this particular course. This is just another way of expressing this mathematical expression. Okay, all this means is I take the antiderivative and evaluate it at b and then subtract it, evaluate it at a. That's what the vertical bar means, written in this particular manner. All right, so let me, before we go on to my math lab exam, let me just show you real quickly here a couple things. Number one, here's just a simple example of the function x squared. This would be the parabola. Okay, so this would be the area going from x equal -1 up to 4. I take the antiderivative, evaluate it at 4, evaluate at -1, take their difference, got to subtract in that order, I get 65/3. Notice Desmos has this built in. I mentioned that before. It's on the calc menu. You just find the integral sign right here, and you just have to hand type in the dx. I could just, as long as I define f of x in an expression prior to this one, I can just type in f of x here. If not, I can replace this f of x with x squared, and it's going to evaluate the definite integral for me. For ones like this, this software does not have the ability to find the antiderivative, so it uses an internal algorithm where they approximate it with lots and lots and lots of rectangles, but not that you have to know that. But what I am, I guess, pointing out here is that it'll give you an approximation. So if I find the antiderivative of e to the x, which is just e to the x, then I'm going to take e to the fourth, right? E to the fourth minus e squared. And I can't simplify that any further if I want the exact value. So all I would need to do is take the e to the fourth minus e squared and then type it into a calculator, and I would get 47.2 approximately. All right. So here are what the problems look like. They're just going to say, and I'm just going to skip these slides here. That was from the ground course, so we don't have time to go over all that. But what I'm showing you here now are some of the problems are worded in my math lab. Okay, so I have here number 2, I think number 6, and I believe number 7. Okay, so all it just says is evaluate the definite integral, simplify your answer. Sometimes it'll ask you to round values here. We'll see why and ones like this. But right now, let's take a look. And then other times they'll ask for the exact value. So, you just got to be aware of what they're asking you to do. So if you type in something else that's correct but doesn't match what their request is, then obviously you're going to miss that problem. Okay. So let's jump on number 2 here. We have a simple polynomial. All right. And all we need to do is take the antiderivative of this quadratic polynomial, which is just this here. I'll try to speak less. This is just the antiderivative. And then I'm going to evaluate it at 1 and subtract the expression evaluated at 0. And notice I have the expression here with the x's replaced with 1s. And over here, I have the x's replaced with 0s. Notice the big set of parentheses, because whatever this is, I have to subtract it. So, again, order of operations tells me I got to evaluate what's inside these parentheses first. When I do that, I end up with 7/3, and that's precisely what we got over here. Okay, so let me go ahead and take a look at number 6, which is this one. Now, if I just ignore the integrand or the integral signs, the upper and lower limit values, I should say, remember substitution, right? We have a composition of functions. So my inner function here is 8 times y to the 9th plus 7. And my outer function is x cubed, so to speak. And notice the derivative of, or at least the form of the derivative of this expression is going to be, y to the 8th. It would be 72 times y to the 8th. Well, I got y to the 8th out here floating around. So let's take a look and see how we would deal with that. So what we'll do here is come over here to this example. Notice we need to get 25/3. They want an exact answer here. So I'm going to let u be my inner function here, which is 8 times y to the 9th plus 7. I take the derivative. You get 72y to the 8th. Remember, I need to be accountable for y to the 8th, and the y, I'm not using the colored pencils right now, okay? So I make my substitution here, the du, okay, over 72, I just wrote 1 over 72 out front, is what's accountable for the y. I should say I'm replacing y to the 8th dy with du over 72. So here's my du over 72, and that's gone. And then I just need to replace my u, so I got u cubed here. And then now I evaluate that interval here from 7 to -1. Now, where is this 7 and -1 come from when I had 0 and 1 up here? Okay, well, quite simply, since I changed my variable from y to u, I have to also change my values for when they're y to what they would be in terms of u. So I come down here, that's what this work is. So when y is equal to -1, if I just plug it in here, I'm going to get u being equal to -1, right? Because if I take -1 to the 9th power, I'll get -8 plus 7. That's going to give me -1. And then when y is equal to 0, of course, u is going to be equal to 7. So I replace my limits of integration here, my upper and lower limits here with -1 and 7. So now I evaluate the antiderivative of u cubed, which is just u to the 4th divided by 4. And I evaluated it 7 and -1. I'm subtracting in that order. Okay. This simplifies to 600 inside the parentheses. And when I divide by 72, I get 25/3 when it all simplifies. And that is the solution that we end up with. Real quickly, I wanted to do another one here. This one gets a little bit more wonky in terms of the notation. If you look at it, it looks pretty intense because now you have a composition with the natural log function as the inner function. So I'm just going to follow my rules, and I'm going to let u be the inner function, which is natural log x, and then I take the derivative of u with respect, so I get 1 over x. And notice I have a form of 1 over x, or the derivative in the integrand. I actually have 12 over x. Okay, so I got to be accountable if u is, replacing the natural log of x, which it is, to the 5th power, then 12 over x times dx, right? So if I come over here and multiply both sides by dx, I get dy, du equal 1 over x dx. Multiply both sides by 12. Now I'm accountable for that, so I'm going to replace this 12 over x dx with just 12 du, and I'm just going to write them in this order to in terms of the multiplication. All right, so I replaced the 12 over x dx with 12 du. I replaced the natural log of x with u, so I have u to the fifth. Now I got to change my lower and upper limits. So again, I just substitute in x, or 1 for x. Natural log of 1 is 0. You can use a calculator to do that, and I get u equal to 0. And then when x is 3, I have the natural log of 3, which turns out to be some decimal. So I'm just going to write the exact value here as the natural log of 3. I don't want to round that value here because once it rounded to 3 decimal places, and remember, when I round here in this computation, it's going to throw off further computations, okay? And we'll see this isn't bad to type into the calculator anyway. So here I got it. I have it 12 times the antiderivative of u to the fifth, which is u to the sixth over 6. I evaluated it at the natural log of 3, 0, which is what I do here. Type all this mess into a calculator here, or I could just simplify. Well, I wouldn't want to do that because that's just 0, right? So really what I need to do is just, I'm just going to do some simplifying here, that the 6 divides out with 12, right, and leaves me with 2. So all I'd have to type in my calculator is 2 times the natural log of 3 raised to the 6th power. And I get about 3.516 when I do that. And notice that is my approximation. Okay. So I simplified this as much as I could, to a reasonable degree. I could type all this in the calculator if I wanted to, but that'd be a little bit more complex to type in than just this expression right here. Okay. So, again, if I went too fast over that, just use your, pause button and your scroll, just scroll to the place and just replay it. And hopefully it'll make sense after a couple times there. And I hope this helps you out. We'll see you next video.